So this is our second lecture in this chapter 5 dealing with the equilibrium of rigid bodies. The first part basically did two-dimensional problems. And we talked about 2 and 3/4 members, but it was primarily 2D. And now we really need to move into 3D. I pointed out last time that the section 5.5 and section 5.2 have exactly the same titles, as well as section 5.6 and 5.3 have exactly the same titles. It's basically two-dimensional problems versus three-dimensional problems. And there's some very interesting information about 2 and 3/4 members in this section, as well as some interesting but challenging information about having excessive constraints or insufficient constraints in this last section, 5.7. So, free body diagram, you have to draw it. You have to learn how to get better at it, draw it, looking to not skip any forces or any other givens like couple moments, and then a bunch of different supports, both in 2D as well as in 3D. This problem I started last time. Let me start it again and solve this problem, okay? So we have a rod, and it supports a weight of 200 pounds, so that's a given weight. Right here is the weight. It's 200-pound weight. And where is the rod? Well, let's say the rod is this part. It goes through, comes out, and it's also this part too. So it's not like a straight rod. It's some mechanism or contraption. It's bent and has a section coming out. Okay. It has a ball and socket at A, so this is A, and it's a ball and socket, meaning that it can't be pulled away or pushed into or slid along from that location A. But the object can rotate. The ball and socket will stop translation, but it won't stop a rotation or pivoting around that point A. All right. It has a properly aligned journal bearing at E. So here's E, and there's a journal bearing. And what do they mean by properly aligned journal bearing is that it will, the journal bearing holds that rod that goes through the middle of it at that location. It will not allow it to move in the X or in the Z, but it would allow it to slide in and out of that bearing. It's not a thrust bearing. A thrust bearing would prevent it from sliding through it or into it further. But this is just an open journal bearing. It would allow it to slide in the Y, and it offers no resistance to rotation of that part going through the bearing. So it would offer no moment to resist the tendency to want to rotate. But if you did not have it aligned properly, it would resist or generate the possibility of a moment that would resist the rotation of the rod that goes through it around the x-axis, as well as it could resist, if it was not properly aligned, the moment around the z-axis or in the direction of the z-axis at E, at that bearing. Again, so this is one of the more complicated constraints. It's a journal bearing, and if it's not aligned, it can have non-zero moments. But if it's aligned, it would have 0 moments. All right. Well, a good way to burn out bearings on shafts is not have things aligned and rotate at high speeds with a lot of power going through it. And then we continue to read. It has a rod from C to D. So here's C, here's D. Now this is a three-dimensional problem, but it's a 2-force member. That C to D is a 2-force member, and it has ball and socket connections at the ends. So that member is only in tension or compression. We talked about 2-force members last time. It's either in tension or compression. So the question is, determine the components of the reaction at A and at E and the compression force in rod C. So right away they say, oh, it's in compression, and so we want to calculate it. So what do we have to do is we have to generate an FBD, a free body diagram. How do we generate a free body diagram? What's one of the steps that you do when you, I have to analyze this problem. I'm looking for the reactions, the supports at A and at E, and I'm also looking for the tension in this member, C to D. Where am I going to get a free body diagram from? What are you going to do to get it? Help me a little bit here, please. You're going to pick something to analyze. You're going to decide, this is what I'm going to analyze. And sometimes it's pretty obvious what you're going to analyze. In this case, the focus of the study, my rigid body, is going to be that bent, non-straight rod. Now, once I've identified that, I have to cut it free from everything else and then isolate that body that I'm focusing the study on. Now, this is really hard in 3D. In 2D, you can redraw your body. In 3D, it's very hard, and so you almost have to reuse the given illustration. So I took and blew this illustration up to try and help to see it. And what do we mean by cutting it? In 2D, I draw an encircling line, but in 3D, it's really a surface. It's not a round surface. It doesn't have to have particular, but it has to cut it. But I'm trying to draw now a surface that's going to completely enclose my object, my body. That's the focus of the study. So, cutting through air, air doesn't exert a force or a torque or anything on my object. But I come over here and I'm going to cut right through this connection at F. Why? There's a chain or rope pulling down, and there's going to be a load, which is the weight. And how much did our weight, how many pounds? 200 pounds? Yeah, 200-pound weight coming down. So I kind of see, oh, I'm going to cut through that, and then I'm going to replace it by a load on my rod at F. Okay, then I cut through air. And this is a tricky one. I have to really cut through that bearing. I got to cut through that support. Throw out the support, but not the rod going through it. The rod going through it is the focus of the study. This is challenging, especially in 3D. Then I back out in air, and I'm going to cut through the ball and socket at C. I could come up and cut through the ball and socket at D, but then it just makes it longer. And let's cut through C. We can continue the discussion about what happens if I cut through D. And then I cut through air, and then I cut through A. And now I know it's a circle in 2D, a line in 2D, but in 3D, think of it as a surface to isolate it. Does that help? All right, this is my rendition of that which has now been isolated. Where is the fixture of the surroundings, the ball and socket at A? It's gone. It's just a point A. Where's my bearing at E? It's gone. I just have the rod going through, and then something is constraining it due to the journal bearing at E. Likewise, this has been cut away, and this has been cut away. Now, can you sketch this on your paper? Do as good a job as you can. Stay with the x-axis, the y-axis, and the z-axis as shown. And now, start putting on there the forces and or moments that need to be, because we cut it free, we have to replace where we cut with reactions due to the supports. Reaction forces and reaction moments. All right? Can you do that, please? So the easiest one would be to go ahead and put the W of 200 pounds on this. That was a load. And do we have any other loads? No, all we have are reactions due to the constraints. The easiest one was this member C to D was, D is up here, but C to D was a two-force member. And even C is connected to that link from C to D at a ball and socket. It's only in tension or compression. That's two force members. So this one we said was in compression. And some of you went ahead and put it like this. So I have a force at C pulling up. But if I did that, think about along the y-axis, wouldn't this thing want to rotate? There would be nothing to stop it from rotating. So it's going to be a force down at C, just like down at W. Now it's hard to draw it where the beginning of the force vector is at the point of application. I think we talked about that before. It's a little confusing to students. It's like, hold it, how come you put the beginning point of the force vector sometimes at the point of application and the head of the force vector in other times at the point of application? But that's just sometimes what we do for clarity. So maybe we call this one tension, not tension. What do we call it? You could put it just F. Call it the force in member C to D. You start introducing some nomenclature. All right, the next easiest one probably is this ball and socket at A. And the ball and socket at A could generate on my object a non-zero reaction force in the X direction, and we would call that A in the X. Maybe A in the X will be zero. Maybe we'll have to conclude that it's zero. But in general, that ball and socket creates a reaction force on my object that could be a non-zero AX. Likewise, you can either put it this way, AY, or you could put it this way, AY. Either one, but it's you got to pick one or the other. Let's put it at the base going out to the head, AY. And then this one is AZ. So there's three potentially non-zero unique components of the reaction at A due to that ball and socket. Another way of saying that, this could be positive, zero, negative. This could be positive, zero, negative, positive, zero, negative. They don't have to be the same value. They're probably not the same value. And then we come over here to E. What did we cut out? We cut out that journal bearing. What does that journal bearing exert on my rod, my body? It could exert a non-zero E in the X and a non-zero E in the Z. It could also exert a non-zero moment at E about the X-axis. But if it's aligned perfectly, like we want our bearings to be aligned, then that will be zero. All right, so for this problem, that was given to be zero, so let's drop it off of our free body diagram or put it on and then explicitly state that that was zero. And likewise up here, you would put it like that and then say, okay, the moment about point E in the Z due to that bearing could be non-zero, but for this problem it is zero because it's aligned. Now let's do a little counting. How many unknowns do I have? AX, AY, AZ, EX, EZ, and the force in the member C to D. I have 6 unknowns. I have at most how many equations for equilibrium in a three-dimensional problem? 6. Some of the forces in the X equals 0, some of the forces in the Y, some of the forces in the Z, some of the moments about some X-axis, some of the moments about some Y-axis aligned with the X and aligned with the Y, and some of the moments around some axis aligned with the Z-axis. Those would be my three equations. All these, have to be equal to 0, equal to 0, equal to 0, equal to 0, equal to 0. What do we call these 6 equations? Equations of equilibrium. And if we're not clear about where they come from and how we're going to use them, we can get very confused easily. So let me press forward here. Here is a cleaned up. All right? And not only do we put them in there, but I found that we struggle with subscripts and notation as well. So here is some subscripts or notation. Just call it F. I chose F without any additional subscripts on it. Here is EX. Does that make sense? EZ. Does that make sense? And then the AX and the AY and the AZ, and then the weight out here. All right. So we have how many unknowns? 6 of them. And we can have up to 6 equations. Now, it's very rare to get a dense 6 by 6 coupled linear algebraic system of equations. But you can do it that way, but it's very rare to have it very dense like that. Often what you can do is you can pick out and get one equation with one unknown if you're very judicious. So what I want to do, and I know some of you know how to do this, but I want you to be really clear and neat and organized and tell me, I'm going to solve for this one unknown using either this force equation or this moment equation, and I'm going to walk around, okay? Talk in your groups to help each other out. Get at least one of these unknowns solved for. All right, so I can pick it up here a little bit. So a lot of us solved for that force right away. And they solved for that force and found it to be 300 pounds. True or false? True. True. How did they solve for the force to be 300 pounds? Some of the moments about the y-axis must equal to 0. And when you do that, what you find just looking at it, that W down makes it want to rotate in the positive sense. So this is going to be W times a moment arm of 1.5 foot. And this F wants to make it rotate in the negative sense. F times a moment arm distance of 1 foot equal to 0. The sum of those two. Does EZ, EX, AZ, AY, AX, any of those contribute? No, because the axis Y goes through the point of application or along the line of action of each of those forces. So only these two forces contribute to the sum of the moments. And using that equation, you get that F is equal to 300 pounds. Now, some other people said, you know what, I love my force equation. Some of the forces in the Y must equal to 0. What does that help us solve for? Another one of the unknowns. AY, some people made that observation. They said AY is equal to 0 from that equation. It's like 2 are now solved for. But don't go back and use this equation and use this equation again. Now, at this point, some people have a strategy for solving for EZ. They can solve for EZ. All right? How many people have a strategy for how to solve for EZ? All right. Can you explain it to me? Do the sum of the moments about the x-axis. It's about the x-axis that goes through the point A. Right? If you do that, does none of these AY, AX, AZ contribute to it? How about EX? Does that contribute? Does that create a moment about the x-axis? No, it's aligned with the x-axis. It's not. But EZ will, with a moment arm distance of 2 foot. And so does it want to make it rotate in the positive sense around the x-axis? Sure. So let me do this. I'm going to do the sum of the moments around the x-axis. That must be equal to 0. That's my equilibrium equation, my general equilibrium equation. For this problem, it boils down to EZ times 2 foot That'll give it a positive sense of rotation. What about this F coming down, this 300-pound F coming down? That'll be negative, let me write it, F times a moment arm distance of 1 foot. And the weight coming down will also make it want to rotate in a negative sense. So negative F, W times 3 foot. And those are the only three. But we already solved for F. We know what W is. We can get one equation, one unknown. We solve for EZ, and EZ is, numerically? Okay. Now, some people, when they're first, they'll put, okay, it's 450 foot-pound force. No, it's not foot-pound force. This is truly a force. It's not a moment. So please be careful when we're writing things out. Somebody says, you didn't put a unit on 0. That's the one case. It doesn't matter. It's like, how much money do you have in the bank? I am flat, busted, broke. I have 0 pennies, 0 dimes, $0, 0. It doesn't matter what currency I have. It's 0 is 0, so units, that's your one case you can leave them off. And it's correct. All right, so now we have those three solved for. Who wants to help me with another one? Okay, you got one? Tell me which one you're going to solve for and then what equation you're going to go and apply. You're going to solve for AZ? Okay, if you solve for AZ, what equilibrium equation are you going to use, knowing already the solution for EZ and F and W is known? Okay, how are you going to solve for AZ? What equilibrium equation? Sum of the forces in the Z direction. So I do sum of the forces in the Z equals 0. I find AZ is positive up plus EZ is positive up. Then we're going to have minus F and minus W equal to 0. Thank you. So now we have, this one is known to be, what did it say, 450? This one is negative 300. This one's negative 200. That's equal to 0. We can solve for AZ. AZ is equal to 50. 50-pound positive. True? There you go. So sort of check, check. All right. How about, so we have 1, 2, 3, 4. I need 2 more to solve for. Anybody else want to contribute? Which one do you want to solve for? Maybe. Okay. EX. How are we going to solve for EX? Perfect. The sum of the moments about the Z-axis. Now you could get any axis parallel to the Z, but here let's just punch it through point A or put it through the origin, okay? So how many people have already done that? Or let me do this. I want you to do some of the moments around the Z-axis goes through point A or through the origin, must be equal to 0, and get me the solution for EX. True? How many people have already done that? All right, so since you suggested it, give me the solution. E of x times 2 is equal to 0. Sometimes our equations are that simple, aren't they? Does EZ contributes no moment, W no moment around the Z-axis, etc. So E of x is equal to 0. All right. Last one, right? We have to solve for AX. What's the strategy for solving for AX? Well, we've used a moment equation, a moment equation, a moment equation, 3 moment equations. You're not going to get it from another moment equation. You get it from another force equation. So we used the sum of the forces in the Y, sum of the forces in the Z. We'll use the sum of the forces in the X equal to 0. And we conclude that AX is equal to 0. Do you agree? Very good. Ready to press forward? Here's another problem. We have a plate. It's a triangular shaped plate. It has a load of 1,500 pounds. So this force right here is 1,500 pounds. It's applied 3 foot out, 2 foot out, if that's marked point in the plate, triangular plate. What type of constraints are there to hold that plate in place? What do we call this? A rope. And the rope is in tension. Okay. And then what do we call this? What does that look like at A? It's a hinge. A hinge. Have you seen door hinges, other hinges? There's a lot of them, but you may not have a lot of experience or analyzing hinges, but let's become more familiar with them. So if I took this triangular plate and this side of the hinge is bolted to the world, and I tried to pull that plate along the y-axis, the hinge would not allow that translation. It would generate a force to hold it in place. True? If I tried to pull it away from this in the x-axis direction, that hinge would have something to say about it. It would hold it there. It would generate a non-zero force to hold it in equilibrium at that location. Likewise, if I tried to lift it, that hinge would have something to say about it. Now, if I took this plate and tried to rotate around the y, what would the hinge do? It would allow it to rotate that plate along this y-axis freely. That's what a hinge does. It's like on a door. It allows the door to rotate. Okay, but if I had this axis, which is parallel to the z, and I tried to rotate it, do you think the hinge might say something? Yeah, it would develop a non-zero moment, couple moment, to resist that rotation of that triangular plate around this axis parallel to the z going through point A, which is the hinge. Likewise, if I said, let's take this plate and try to rotate it around the axis that's parallel to the x, goes through point A, guess what? It's going to generate a possible non-zero moment for that reaction. So that's what that hinge does. It can have 1, 2, 3, 4, 5 non-zero reactions or resultant forces and moments because of resisting the plate's desire to translate and rotate. So, okay. So the question is compute the tension in the cable, maybe use T for tension, and the components of the reaction at the hinge. So we're going to be looking for A, 3 forces, AX, AY, and AZ. That's our 3 components of our reaction force at the hinge A, as well as the moment at point A about the, let's go here with the x-axis first, and then the moment about point A parallel to the z-axis. Those are 2 reaction moments that could be non-zero. What about this other one? Sorry, the hinge rotates freely, doesn't resist that rotation. Okay? So we've identified or picked some object to analyze. It's obvious in this. It's a plate. That's our plate. You have to cut the plate free from the rest of the world. When I cut the plate free from the rest of the world, I have to cut through B, and I cut through the hinge, and then I cut through a bunch of air. That's only 2 places where I cut through supports, at the hinge A and then the cable that's tied to B. Then I replace where I cut through the supports with my reactions at the supports. So you cut it free, right? This is point A. This is point B. If I put a tension on, I should only put it in there. It's only acting in the Z direction, isn't it? It's not like I put a BX and a BY and then a BZ. No, it's just one there at B, and I know exactly its direction, and that's the unknown tension in the cable. Likewise, I come out and do the same thing at this point A. Well, I think I've done that, so let me show you. Here's a rendition. Does it look okay? Does it look like I've done it okay? Now, this is one thing to draw the arrows and the little vectors representing the moments at the point, a couple moments, but I want to now label it. This is a little challenging. I want you to label each one of these. I already did this one. I said, oh, this one's T. True? So that one's pretty easy. It's given to you. That's T, tension. Label these other ones. 3 red vectors, 2 curled blue vectors. True? Label it for me, okay? All right, so in the interest of time, I'll pick it up here, but I was trying to get you to make sure and put AZ. What exactly does AZ represent? The magnitude of the component, the reaction, or supporting force at point A in the direction Z. Why don't they put like FAZ? You can, and some books may. But this text just says, look, we're going to call it as short as possible, just A subscript Z, then A subscript X, A subscript Y, and then we have the moment at A in the X direction, and the moment at A in the Z direction, and then we have the tension over here. We have a clean free body diagram. We have our load shown on it, whatever that load was. How many pounds was that load? I forgot. 1,500. 1,500 pounds. We have dimensions on our free body diagram. 3 foot, 9 foot, etc. We have our coordinate system identified, X, Y, Z, and back here is the origin. And we have our reactions due to the supports. And those are unknowns. So, let's figure out how I'm going to start solving for some of these unknowns. How would you solve for the tension? Is there any way to get the tension with one equation and one unknown before I know any of these AYs or MXs or anything like that? Is there any way to do that? Maybe, maybe not. There is. All right. How would you do it? Some of the moments about the y-axis. That's extremely insightful. So if you do the sum of the moments around the y-axis, going through point A, we have in the positive sense F times a moment arm distance of 3 foot, and this tension, it will give it in the negative sense, negative tension times a moment arm distance of 9 foot. Now what I should have done is I should have said my equation is that the sum of the moments around the y-axis must equal to 0 for equilibrium. I should have said that somewhere. And then I said, for this problem, this is what it looks like. Hence, we solve for t. And when you solve for t, what do you get? 500 pounds. True? All right. Whew. Anybody else want to pick one and say how you're going to solve for it? We got AY, AZ, AX, moment of at A about the x-axis, moment A about the z-axis. AZ, you're very good. Do the sum of the forces in the z direction must equal to 0. And we have the tension up, we have the load down, and we have AZ up, and that's equal to 0. When I say up, I mean positive direction. I think you follow. And then what do we find for the AZ? It's going to be F minus T. And so we find that AZ comes in at 1,000 pounds. True or false? Very good. Another one. Who wants to, somebody new, who wants to volunteer? So it says for equilibrium, the sum of the forces in the x direction must equal to 0. That gives us an equation that AX, that's the only contributor, must be equal to 0. Bingo. Somebody else. New. Did you do one before?
Yes.
All right. Sorry. Somebody else. Go ahead. So we're going to do the sum of the moments around the z-axis. All right. Now let's be clear. You can do the sum of the moments around the z-axis that goes through the origin, or you could do the sum of the moments about the z-axis that goes through point A. Okay. Now, both of those axes through the origin or through point A, this will contribute no moment because it's aligned with both. This will contribute no moment because it's aligned with both. They're parallel. They're all parallel. AZ will contribute no moment. What about the XZ about the Z-axis? Would that contribute a moment? If it was non-zero, it would. True? How about AY? Well, its line of action goes through both of those, so it would contribute 0 for both. All right? So let me do this. Let me write it two ways. Sum of the moments about the z-axis that goes through 0, the origin, that must be equal to 0. What equation does that give us? That gives us AX is going to make a negative sense of rotation times a moment arm distance of 3 foot. That's contributor here, true. And then we're going to have a plus the moment AZ equal to 0. Did I do that equation correct? Did I leave anything off? All right, let's do this equation. Sum of the moments about the z-axis that doesn't go through the point O, the origin, but goes through the point A. What? Can I do that equation? Will that work? Sure it will. Let's try it. So we have that the moment AZ is equal to, does that make sense? All right. Is that where you were leading me? You did it? Is that okay? All right. How about the moment A in the x-axis, that one? Some of the moments about the x-axis. Let's go ahead and do that. Some of the moments around the x-axis. But the x-axis can either go to the origin or a logical place would go through point A, either one. Which one do you want to do? The origin? Must equal to 0? Okay, let's do it. Some of the moments about the x-axis going through the origin. Does T exhibit or contribute? No. Does F contribute? Yes, it does. And is it a negative F times a moment arm distance of 2 foot? All right. Is that right? All right. Does AZ contribute? AZ. Yeah. And that's going to be a positive AZ times a moment arm distance of 3 foot. Does AX contribute? No. Does AY contribute? No. Does the moment of A about the x-axis contribute? Yes. It's the moment A x-axis equal to 0. So we previously solved for the AZ. That was 1,000 pounds right up here. And we know what our load is, F, 1,500 pounds. The only unknown in this equation is the moment at the point A about the x-axis going through point A. And we solve that one, and we find that it's equal to 0. True? Okay. So, are we done with this problem, or do we have one more to solve for? Which one do we need to solve for? AY? All right. How do we solve for AY? Sum of the forces in the Y. And when we do the sum of the forces in the Y must equal to 0 for equilibrium, we conclude that AY is equal to. So 1, 2, 3, 4, 5, 6. That's it. We're done. These problems don't end, but that's the way you get good at it, right? So I have a floor crane. It has a weight of 250 pounds with its center of gravity at location G. So I look for the location G in my illustration. So at this point G acting down, but you say G looks like it's floating in the air and isn't in the middle of a chunk of metal as part of the, that's right, your center of gravity can be in the air, kind of like if I had a pipe like this, it was bent, right? And I said, where's the center of gravity of that pipe? It'd probably be around there. It's in the air, not on the pipe. But this is the same thing here, the center of gravity right there, G. Determine the largest load F that the floor crane can support without what? Overturning. That would be a not very good event, right? You ever been out on YouTube, looked at some videos of cranes that tip? They're a little exciting, except for the operator in the crane when it tips. Then it's not so exciting for them. But this can happen where you can overturn your floor crane. All right, so what is that largest force load at which it at the point of overturning, and what are the reactions at the wheels, which are smooth? So how many wheels do we have? A wheel at A, wheel at B, and a wheel at C, right? And so what are those reactions at the smooth wheel at that point of tipping or overturning? All right? Make a free body diagram, cutting the object away from the surroundings. True? This one's a little harder to cut it away, make it look pretty. I'd come in and I'd say, well, I'm going to cut under that wheel, and there'll be a force acting up. We'll call it A, and the Z, if you want to put a Z on it, and cut, and there would be a force B up in the Z, and a force C up in the C. We have the weight coming down, W, at G, and we have the load at F. Does that look like a decent free body diagram? Maybe you want to count your unknowns. What are your unknowns? How about we don't know what the largest load F is. We know the weight, that's 250 pounds, so that we don't need to, we can put it over here, W is equal to 250 pounds. How about the reaction support at the floor A, pushing up on the bottom, the B, and as well as C? Do you see more than 4 unknowns? Okay. So what I want you to do is to, as a team, figure out how to solve this problem. I don't want to give too much away. You see how far you can go with this problem. All right, I was struggling not to give too big of a hint, but I think I need to. There's a key idea in this problem that you haven't seen before in this class. It's this idea of overturning, tipping. Once you see, oh, this object is about ready to tip, one of these 4 forces on my free body diagram representing the object about ready to tip is equal to 0. That's a big observation. Yeah, and you almost have to first, see a few tipping problems like, oh, that's what happens when you tip, right? Nothing at the floor is going to hold that point down. Yes? It's an observation. At the point of tipping, C will be equal to 0. And I don't know how to explain it other than the way I just tried to explain it. Because it's a smooth surface, a roller. It's not like a ball and socket. It can't be held down. The wheel can lift off of the floor, and that's what'll happen when it tips. And so right at the point of tipping, C, the force is equal to 0. Now you can solve for the problem, I bet. All right, so let me jump in here again. Sorry if I wish we had more time, but if you wanted to solve for F directly, do the sum of the moments around the line that's parallel to the y-axis, but it doesn't go through the origin. It goes underneath the points A and B. Why? Because if you go right underneath the wheels at A and B, what is the reaction force A and B? How much moment do they generate around that line? 0. And so the only thing that generates a moment is the weight wanting to rotate in the negative sense. This is the positive direction of that y-axis translated over underneath wheels A and B. And then the force F that makes it want to rotate in the positive sense. So the only challenge is to try to find this distance right here such that the line of action of F comes down. What is that distance? You calculated, didn't you? Yeah, it's kind of an interesting calculation. You have a right angle here, you have 10 foot, you have a 30-degree angle. So what is this distance right here? 10 foot times cos of 30. And then that was from the origin, and we know that 6 foot is to get to this line. So this distance right here is 10 cos 30 minus 6 foot. A little bit of work, right? But that's our moment arm distance for the force F. And then the moment arm distance for the weight that goes through G around this axis is, what's that distance? It'll be, I think they give it to us, 4 foot right there. Isn't it? 4 foot. All right, is that how you solve for F? Yep. Okay, and then you got for F a value of 375-ish, and it's pounds. And I know there's another digit or so on there, but 375 pounds. 376 pounds, I think, if you round it off, round it up. Okay, again, how did we get that? Sum of the moments about the y-axis, or an axis, a y-axis that goes through points A and B. That's a long subscript, isn't it? But I'm trying to be clear what I did, okay? All right. Okay, now the other one is how to solve for A and B. Somebody said do the sum of the moments around the x-axis, sum of the moments around the x-axis equal to 0, and you conclude that A is equal to B, right? And then what's the last one that they need to use? Yeah, you can do that. You can do that to solve for the A's and the B's. Or the easier one, just say the sum of the forces in the z direction is equal to 0. So I have the load down, I have the weight down, and I have A up and B up. And we just said A is equal to B, so 2A is equal to W plus F. And I know there's multiple ways. What you described is fine, but you find that the A is equal to 313 pounds and B is 313 pounds. And I see a couple people had done the whole problem. Maybe your thought process was a little different, but I think we're good on this, okay? Look good? What did we really knew? What was new on this problem? The idea of tipping, and one of those forces goes to zero. Oh, there's a nice clean free body diagram. The shaft assembly is supported by two smooth journal bearings at A and B and a short link C to D. So here's our journal bearing. It can allow it to rotate along the x-axis, no problem. But if that shaft wants to move in the y, there'll be a reaction force to keep it there. Or if it wants to translate in the z, it'll be a reaction force to keep it there. Now this other one is it can slide in and out. There'll be no reaction force in the x because of that bearing. It's not a thrust bearing. They do make thrust bearings. There's a little difference. Okay. That's what the journal bearings. Okay, and then we have that short link. What about the connection between this link C to D and where's, okay, here's our link C to D, right? So D looks like it's pinned to the rest of the world up here at D. All right. And then C looks like it's connected at that point right here. It looks like it's pinned there too. All right. What about, what is this shaft and this part and this little peg part, are they connected or are they all loose? Can they slide and rotate amongst themselves? What would you guess looking at that illustration? Like this is a little peg, this is a little bracket, this is a little rod. What can this rotate on the rod? Is that what they're showing? Not really. It's as if this is welded. This is welded. Okay? Right? Okay. So now, if a couple moment is applied to the shaft as shown, there's a 250 Newton meter couple moment applied. If this is the positive x direction, is that a positive sense of rotation around the x-axis or negative sense of rotation for this couple moment? It's a negative. Negative, isn't it? Determine the components of force reaction at the journal bearings and the force in the link. So there's a force in the link and the reaction at the journal bearings. The link lies in a plane parallel to the YZ plane. So here's our YZ plane. It's not perfectly in the YZ plane because a little offset, right? It looks like this is in the perfect YZ plane, but this one, C to D, is offset a little bit, but it's still parallel. And the bearings are properly aligned on the shaft. Properly aligned. There's no reaction couple moment in those bearings. So, first things first, I have to pick something to analyze. Then I have to figure out what I'm going to solve for. I'm solving for this member right here. First of all, can you use some insight and tell me, is that member C to D a two-force member? Looks like a two-force member. So that member is only in tension or compression? Given the way the load is applied, is that member going to be in tension or compression? In tension. You're exactly right. Tension. So we're going to solve for the tension up here, and then we're going to solve for these components of the force reaction. That's kind of interesting wording. We've seen it a couple times, but it's basically like if this is location A, it's like location AX, force AY, and then the force AZ, possibly up to that. But we just said that it could slide in the X freely through that journal bearing. So AX is 0. I'm just going to not even have it in my free body diagram. But I have two components of the reaction force at A. Likewise, I come out to B, I would have 2 components. True? So I cut, go circle, cut, come up here, cut, like that, and then come down, and I generate a free body diagram. And I try to clean it up, and I try to put my reaction supports in there. And so I put in an AY and an AZ, but not an MAZ. Why? Because it's 0 because of the problem says it's 0 because it's aligned, properly aligned. And then I don't put in an X either. All right. So, how do I solve for some of these? Yes? Well, this angle right here of being 30 degrees rotated is I'm going to have to remember that. And then this coming off of here is at an angle 20 degrees up. F is at an angle 20 degrees up from what? Well, you have to be careful. This line is parallel with the Z. This line here, this line right here is parallel with the y-axis. So, you know, this problem would be easier if it's 30 degrees, 30 degrees, but it wasn't. It's 20 degrees, 30 degrees, so be careful. Okay, let's do this. Do the sum of the moments about this. Sum of the moments about the x-axis must be equal to 0 for equilibrium. True? Write that for this problem, for this free body diagram. Does AZ contribute to the sum of the moments around the x-axis that goes through the origin? No. How about AY? No. How about BZ? No, no. Guess what? Only one does, F. As well as this applied couple moment to the problem. So this problem boils down to, for this problem right here, this equilibrium equation, is that we're going to have the I'm going to put over here 250 Newton meters, making it want to rotate in the negative sense, and then F making it want to rotate in the positive sense. How am I going to get the magnitude of the moment that F wants to make it want to rotate in the positive sense? That's the hardest part of this problem. At this point right here, if I decomposed it into a component that went directly, let me try and draw this a little better, that went directly through that axis, and then I had another component that was perpendicular to that axis, but it's going to be perpendicular like this, right? Because of the 30-degree slope of that arm. Hard for me to show that. It's like if I moved this force over to this point, maybe it would be easier without that little peg. And then this line coming down, right, I would say I'm going to decompose that force into one that's kind of pulling up and one that is perpendicular. We have F. Then we're going to have the cosine of the difference between 30 and 20 degrees, 10-degree angle. That's what it is. And then we're going to have the perpendicular distance of 0.25 meters. Where'd that come from? Right here. This allows us to calculate for F. And then when you solve for F, you 1015 Newton. That was the hardest part of this problem. How about this? If I do the sum of the moments around the y-axis that doesn't go through the origin, but if I put it through point A, that also has to be equal to 0, doesn't it? So why did we put it through point A, the y-axis going through point A? So that none of the forces at A contribute. All right, I have to work on this F. Does it contribute anything about the y-axis? Does it contribute any moment around this y-axis going through point A? Yes? It's this upward component right here. Tried to show it right there. And it has a moment arm distance of 400 millimeters minus 120 millimeters. So what is that upward component? F times the sine of 20 degrees times a perpendicular distance of 0.4 minus 0.12 meters. And that's going to contribute a sense of up. And then what about BZ? That's a positive sense of rotation too. BZ times a perpendicular distance of 0.7. That's equal to 0. Where's the 0.7 come from? 0.4 and 0.3. So we find BZ is negative 139 newtons. What does the negative sign mean? It's in the opposite direction of what was assumed on our free body diagram. If you do the sum of the forces in the Z must equal to 0, then you find that you can solve for AZ. It'll have both BZ, AZ, and then a component of that force is in the Z direction. And you find that it's negative 208.4 newtons, or 208 newtons. All right. So we've solved for this one, this one, this one. We have to do the AY and the AZ. I'm sorry, the AY and the BY. All right. Well, if you don't want AY to contribute, could I do something like this? What is that? Some of the moments about the Z-axis that goes through point A. All right. Let me just give the answer that the BY, a little bit of math there, is 382 newtons. And then the last one, what about the sum of the forces in the Y direction? I'm running out of room, so I'll just erase here. And then we have the sum of the forces in the Y direction must equal to 0, which gives us an equation of equilibrium. And then the force AY is equal to 573 newtons. Well, maybe that wasn't the best idea to start such a challenging problem so close to the end of lecture, but there you go. Thank you very much.